Good afternoon, dear students. My name is Nigar Çarşıbaşı. In the scope of Chemistry 102 course, today I'm going to investigate and we will going to study the chemical equilibrium and the factors affecting equilibria. Now we know that few reactions proceed in only one direction, and most reactions are equilibrium reactions. So what is equilibrium? Let's define first the equilibrium. Equilibrium is the state in which we observe no distinct changes in our system. We have no observable changes as the time goes by. And chemical equilibrium can be achieved when the concentrations of the reactants and the products are essentially constant. And at this point, the rate of the forward and the reverse reactions are equal. Equilibrium can be a physical equilibrium, which is for a single substance between two different phases. Like you see here for water. Liquid water can go into gaseous water by evaporation. And in turn, the gaseous water can condense back to liquid water. So this is the same substance between two phases. We call this the physical equilibrium. Coming to the chemical equilibrium, in this case, we have a reaction going on. So the reactants are converted to products, so you have different species now. For instance, in the case of the nitrogen tetroxide, which is a colorless gas, this is converted to nitrogen dioxide gas, which has a dark brown color. And we can observe a color change as the reaction proceeds. And this is a chemical equilibrium then. So how can we determine the value of equilibrium constant? What is equilibrium constant? Let's investigate this first. For the same reaction for which the nitrogen tetroxide goes to nitrogen dioxide, starting with different concentrations, experimental data are recorded, because equilibrium can be only investigated in terms of experimental means. For instance, in the first case, look at the graph. You have no nitrogen tetroxide, you start with only nitrogen dioxide. And what happens? Nitrogen dioxide is consumed with respect to the reaction, and nitrogen tetroxide is being formed. As a result, at a certain point, when the equilibrium has been reached, the concentrations remain actually constant. Starting with another initial concentration, this time you start only with the nitrogen tetroxide and you maintain a new equilibrium position with different concentrations. And you can also start with both nitrogen dioxide and the nitrogen tetroxide, as you see. And investigating the data, we observed that this ratio, nitrogen dioxide concentration to the square divided by the nitrogen tetroxide concentration, is essentially constant with different experimental data. So we can conclude that this value is an important value, and it is called actually the equilibrium constant. So whatever your starting concentrations are, the value of the equilibrium constant is essentially the same. And another important point in here is that the exponent appearing on the concentration is the same exponent with the stoichiometric coefficient. For a general reaction, we can write the equilibrium constant like this: the products raised to exponents equal to the stoichiometric coefficients appearing in the reaction divided by the reactant concentrations to the exponent equal to the stoichiometric coefficients again. Okay, this is the same graph as I showed in the previous slide. You can also investigate the reaction proceeding from the color change. Because I said that nitrogen dioxide has a brown color, whereas the nitrogen tetroxide is colorless. For instance, for this case, when you start with nitrogen dioxide only, which has a brown color. As the reaction proceeds, you are going to see that the color gradually will fade because nitrogen dioxide is being consumed. On the other hand, in the second part, if you start with dinitrogen tetroxide, you are going to see that as more nitrogen dioxide molecules are being formed, brown color will appear. In all cases, as a result, if we summarize until now, in all cases, whatever your starting concentrations are, the equilibrium will be maintained with the same value of equilibrium constant. And this is the point in which the reactant and the product concentrations remain essentially constant. They are still ongoing, but the forward and the reverse rates will be equal at equilibrium point. Now let's investigate the relation between chemical kinetics and the chemical equilibrium. You can consider this reaction as an example which proceeds in a single step in both forward and reverse sides. A plus 2 molecules of B are converted to AB2 compound. So Kf here is for the forward rate constant, and Kr is the reverse rate constant. So if you put the rate expressions for forward and reverse rates, you are going to obtain these expressions. So what did we say? At equilibrium, the two rates, forward rate and the reverse rate, should be equal. If you equate them, you are going to obtain that the forward rate constant divided by the reverse rate constant actually gives us the equilibrium constant Kc. So you can see that since these are constant, the value of equilibrium constant is also a constant regardless of the concentrations. So equilibrium concentrations can change, however, there is a single value of equilibrium constant at a certain temperature for a specific reaction. Okay, how about the magnitude of K? What does the magnitude of K tell us in terms of the reaction proceeding? So, a huge value of K, meaning that K value is much higher than 1, for instance. This shows us that the reaction favors the product side, and the reaction will lie to the right, the product side. However, a very small value of K, this will show that the reaction doesn't favor the product side, but it favors the reactant side, and it will lie to the left, as you also see in this figure. So what do we mean by a huge value? For instance, K values greater than 10 can be regarded to be big value of rate constant, and this shows that the reaction favors product side more. And a small value we mean, for instance, K values less than 0.1, and they maintain the favor of reactant side, and the equilibrium will lie to the left, to the reactant side. And you see here, for the general case, we can also write the equilibrium constant like this. And so the value of the equilibrium constant is important. It tells us which side the reaction favors. And at this point, I will mention that we do not include any unit in the value of the equilibrium constant, because the value of equilibrium constant is of importance for us. Now, we are going to investigate the factors affecting chemical equilibrium. Actually, we mean here the Le Chatelier's principle. Le Chatelier's principle basically states that if an external stress is applied to a system which is at equilibrium, the system tries to offset this stress. How? By reacting in such a way that it will just overcome this stress, behaving in an opposite way. And what do we mean by a stress? This may be a concentration change, this may be a pressure or a volume change, or it may be a temperature change. And so in all cases, the system will react to offset the change that I have made. Okay, first of all, let's investigate what do we mean by a concentration change. Consider this reaction, which is the formation of ammonia, gaseous phase. In the gaseous phase, nitrogen plus 3 moles of hydrogen is converted to 2 moles of nitrogen gas. Assume that initially your system is at equilibrium. As you see, the concentrations are constant initially. And suddenly you add more ammonia to your system. Now what happens? Of course, you disturb the equilibrium. Now, the system will try to maintain the equilibrium back. How? It will try to offset this change that I have made. It will try to consume the ammonia that I have added. That's why the equilibrium shifts from this side to this side, to the left. So it will consume ammonia and more nitrogen and hydrogen will be formed. As you also see in the graph, so you put some ammonia to your mixture and the reaction will proceed to the left-hand side where the ammonia concentration will drop, hydrogen and nitrogen concentrations will increase until the system reaches a new equilibrium state. Now, let's summarize the change in concentration for a general reaction like this. If you are adding products to your system, for instance, you are adding C or D, whatever. So the system, according to Le Chatelier's principle, will react in such a way that it will try to consume these added products. That's why it will shift to the left. So if you increase the concentration of products, the equilibrium will shift to the left-hand side. Now, how about if you remove the products formed? You are removing some product from your medium. Then the system will try to produce more product. So the reaction will proceed to the right-hand side. And if you decrease the concentration of products, the equilibrium will shift to the right in order to produce more products now. Similarly, the same procedure can be carried out for reactants. If you add more reactant, the system will shift to the right, the reaction will proceed to the product side, and if you remove reactants, the equilibrium will shift to the left-hand side in order to produce more reactant. Okay, we covered concentration change. Now let's come to volume and pressure change. So you know that solids and liquids are incompressible, which we mean that pressure does not have a contribution effect on the for gases and solids. That's why you have to have a gas in order for the volume and the pressure have an effect. So for solids and liquids, gas change in pressure or volume doesn't have a considerable effect. That's why we have to investigate a gaseous form reaction. Now, what happens, for instance, in this gaseous phase reaction if we increase the pressure? So, Le Chatelier's principle says that the system will try to offset this change. How? So, reacting in a negative way, it will try to decrease the pressure. How come can it decrease this pressure? It will shift to the right where there are fewer number of moles of gas. So this is to the right in this case, because you have 2 molecules of gas on the left-hand side, you have 1 molecule of gas on the right-hand side. And if you increase the pressure, the system will try to decrease this pressure in such a way that it will shift to the side where there are fewest moles of gas. How about if you decrease the pressure, then the system will try to increase the pressure. How can it increase the pressure? It will shift to the side where there are more number of moles of gas molecules, which is in this case the left-hand side. So, how about increasing volume? So you know that according to ideal gas law, pressure and volume are inversely proportional. So if you increase the pressure of a system, its volume will decrease, or if you increase the volume, the pressure will decrease. That's why increasing the volume has the same effect like decreasing the pressure. Increasing the volume will shift to the side where there are more moles of gas, and this is in this case left-hand side. And decreasing the volume has the same effect with increasing pressure, because we said that they are inversely proportional. That's why it will cause the same effect. It will shift the equilibrium to the side with fewest moles of gas. Okay, now we can check this example. If you look at the examples, it says you have different equilibrium systems. Can you predict the direction of the net reaction in each case as a result of increasing pressure? So we said that increasing pressure or pressure has an effect only for gases. So if you have solids or liquids in the medium, you are not going to consider them. Looking at the first case, case A, you have solid on this side and solid on this side. You will not consider them. You are only going to focus on the gas molecules. You have 3 mole gas molecules on the left-hand side, on the reactant side, and 2 moles of gas molecules on the right-hand side. So if you increase the pressure, the system will shift to the side where are few number of moles of gas molecules, which is in this case to the right. And in case B, you see that you have 1 mole of gas in this side. However, you have 2 moles of gas in the right-hand side. So if you increase the pressure, the system will try to decrease the pressure, and it will shift to the left where there are fewer number of moles of gas molecules. How about in the third case? Since you have equal number of gas molecules on the left-hand side and right-hand side, there won't be any shift, so it won't cause any effect. And the other change or other stress effect that we are going to investigate is the temperature effect. So how does the temperature changes the system's dynamics or equilibrium will depend on whether the reaction is endothermic or exothermic. So for endothermic reactions, the heat is absorbed from surrounding. So heat is like a reactant for endothermic case. How about for exothermic case? In exothermic reactions, heat is produced. So heat is like a product for the exothermic reactions. And if you increase the temperature, if your system is endothermic, then what will happen? According to Chatelier principle, if you are giving heat to the system will try to use this heat and shift to the product side, and K value will increase, as you see. The reaction will proceed to the product side, and that's why also, since the value of K depends on temperature, the value of the rate equilibrium constant will also increase. However, in the case of exothermic reaction, the shift will be to the reactant side. That is why equilibrium constant will decrease. And for the case of decreasing temperature, for instance, you are cooling your system, then the system will try to produce more heat. So this will be in the case of exothermic case, right? The exothermic case produces heat. That's why if you decrease the temperature, the system will shift to the product side where there are more heat produced there. And the last one, maybe we can also investigate the effect of a catalyst. So a catalyst is a compound that does not appear in the reaction expression, but it enhances the reaction rate. How? Actually, it lowers the activation energy for a reaction. So you know that for all reactions, there is a threshold energy, which is called the activation energy. The reactants should have this energy in order to be converted to products. So what does a catalyst do? It actually, as you see, as you compare the two pictures, this is uncatalyzed reaction, and this is the same reaction which is catalyzed. The catalyst actually decreases the activation energy. That's why it makes the reaction to be faster, and it will reach equilibrium sooner. However, it doesn't change equilibrium constant. It doesn't also cause a shift in the position of an equilibrium system. It just maintains the system to reach equilibrium sooner. A catalyst lowers the activation energy of both forward and reverse reactions, as you know. As a result, the ratio of them will cause no change. It won't have an effect on equilibrium constant, also on the shift of equilibrium. Okay, let's summarize with this table. What did we see until now with the Chatellier's principle? So, concentration has an effect, yes, on the equilibrium shift. It will shift either to the right or left, depending on the reaction. However, it has no change on the value of equilibrium constant. The only effect that changes the value of equilibrium constant is temperature. So, pressure similarly shifts the equilibrium, yes, to the right or to the left, depending on the reaction and the effect you make. However, it doesn't cause any change on the equilibrium constant. Volume similarly shifts the equilibrium, but does not affect the value of equilibrium constant. The only thing is temperature. Yes, temperature affects the value of equilibrium constant. How about catalyst? We said that catalyst has no effect on both the equilibrium and the value of the equilibrium constant. Now, I'm going to show you a video, actually an animation showing the Chatelier principle. So, according to Chatelier principle, we said that if you make a stress to the system, it can be change in concentration, it can be change in pressure, it can be change in temperature. The system will try to offset this change. Now we are going to investigate how, for instance, the concentration change affects our system. Okay, here the system we study is iron thiocyanate decomposing into iron plus 3 and thiocyanate ions. So you see our reaction medium here, and the atomistic view, the microscopic view, can also be seen here. So iron thiocyanate has a reddish color, and iron plus 3 has a yellow color. So assume that at equilibrium you have the following concentrations of each of them. Now we are going to investigate what happens, for instance, if you add more thiocyanate ion, or if you remove some iron plus 3 to the system that is at equilibrium. First, adding more thiocyanate. You see that thiocyanate ion concentration has increased. Now, system will react in such a way that it will try to consume this added thiocyanate. That's why the reaction, the equilibrium will shift to the left, where you are producing now more iron thiocyanate. As the color of the reaction medium also implies, more iron thiocyanate is being formed. You can also, in the atomistic view, see the number of moles of molecules that is forming in this change. So we saw that the reaction, the chemical reaction, shifted to the left to maintain a new equilibrium. And how about if we remove some iron plus 3 ions? You see, I'm removing from the medium some iron plus 3. But what will happen this time? The equilibrium will be maintained, or the system will try to offset this change by forming more iron plus 3 ions. That's why it will shift to the right. As also you can see from the color change of our reaction medium, as more iron plus 3 ions are being formed, the color will get yellow. Also, you can see more iron plus 3 ions are being formed now. And you can see that iron thiocyanate concentration drops, whereas the others are increased since the system shifted to the right. Now we are also going to investigate the change in pressure and also the change in temperature. Let's look at the change in pressure first. As we said, we have to consider a gaseous phase system for the investigation of effect of pressure. So this is molecular iodine, which is decomposing into atomic iodine atoms. So molecular iodine has a purple color, whereas atomic iodine is colorless. Assume that at equilibrium we start with these concentrations. And now we are going to increase the pressure of the system and observe what will change. So now I'm increasing the system's pressure. According to Chatelier principle, the system will react in such a way that it will try to reduce this temperature increase. As you see, I press the piston, I increase the pressure, volume has decreased. Now the system will try to decrease the pressure. How? Shifting to the side where there are less number of gas molecules, and in this case it is to the left. So as you see from the color of the reaction medium, it is getting darker. The intensity of the purple color is increasing. Why? Because the system shifted to the left and more iodine, molecular iodine, is being formed. Now, how about if you do the reverse? If you decrease the pressure now. I am decreasing the pressure by taking the piston up. The volume is increased. Now what will happen? I am just decrease the pressure and the system will try to increase this pressure in such a way that it will shift to the right where there are more number of moles of gas molecules, which is in this case this side. As you see, there is 1 mole, there is 2 moles of gas. It shifted to right hand side. And what happened to our color? Since more atomic iodine has been formed, the intensity of the color diminished. It got lighter. As also you can see from top the atomistic view of the atoms in the reaction medium. So what is left? Now we come to the temperature change. So coming to the previous reaction, the nitrogen tetroxide going to nitrogen dioxide. So nitrogen dioxide has a brown color, but the nitrogen tetroxide is colorless, we said. So this is an endothermic reaction, and starting with these concentrations. Now what happens if I increase the temperature or decrease the temperature? Let's investigate this first. Now first of all, I will increase the system's temperature and investigate both the color change and the shift in the equilibrium. So you see, I'm heating my system, I'm giving heat, increasing the temperature. So since this is an endothermic reaction, I can put heat like a reactant to the left hand side, like this. And if I am putting heat, the system will react in such a way that it will try to consume this heat. That's why it will shift to the right. So as more nitrogen dioxide, which is brown, is formed, you are going to observe that the intensity of the color will be darkened. So more brown. In the case of heating, how about decreasing the temperature now, the vice versa, negative effect. So I'm decreasing, I'm cooling my system, I'm removing heat. So the system will react in such a way that it will try to produce heat. So which side the heat is produced? In the left hand side. That's why the equilibrium will shift to the left. And you are going to see that the brownish color will get lighter. It will go to colorless, since the nitrogen tetroxide is now more being formed. So actually this is the end of this lecture about chemical equilibrium and Le Chatelier principle. Let's meet in another lecture in the following weeks. Bye.